Hello, everybody. My name is Ranjan Laha. I'm an assistant professor in the Center for High Energy Physics, Indian Institute of Science, Bengaluru, India. I am a theoretical astroparticle physicist, and I work on various topics on dark matter, neutrinos, gamma rays, beyond the standard model physics in general, and things on particle physics, astrophysics, cosmology. Today, in this Neutrinos from Home conference talk, I'll be talking about our recent work where we studied how high energy neutrinos from the sun can be used to discover dark matter electron scattering. This is the recent work that I've done with my collaborators, Taroknath Maiti, Akash Kumar Saha, and Shagnik Mondal. So here is the contents of my talk. I'll first introduce dark matter electron scattering. Then I'll tell you how the capture of dark matter in the sun can happen via scattering with electrons. I'll talk about how one can search for dark matter electron scattering interactions via high energy neutron observations from the sun. And then finally, I'll conclude. Right. So it is well known from various astrophysical and cosmological observations that the presence of dark matter is well established. However, we still do not know what is dark matter or what is the dark matter candidate. The dark matter candidate can have a wide range of masses. The lightest dark matter candidate can have a mass of approximately 10 power minus 22 eV, and the heaviest dark matter candidate can have a mass of, say, a few hundred solar masses. I think it is important at this juncture to emphasize that we need to thoroughly test all well-motivated dark matter candidates, which implies that we must test all regions of dark matter parameter space and various couplings between dark matter particles and standard model particles. The focus of this talk will be to probe dark matter electron scattering. So dark matter electron scattering is something that has taken off over the last 15 years. So this is this plot that you can see is the latest plot about the parameter space of dark matter electron scattering that is being probed by various experiments. The dark matter mass is on the x-axis in MeV, and the dark matter electron scattering cross-section is on the y-axis in centimeters square. There are various lines, but let's concentrate on a few important lines here. This line that you see marked as Sensei at Snow Lab, this is the limit from the Sensei experiment. Anything above this line shaded is ruled out. We also have this line marked dark side 50. Again, anything above this line is ruled out. And then finally, we have the xenon 1 ton S2 only analysis. Anything above the line is ruled out. There are also various other lines, which is not yet immediately relevant. And there's also some theory models which are being shown by these colored lines. And this also assumes a particular dark matter form factor. What we learn from these plots is this is a region of parameter space which is heavily explored, and people use various targets. People use silicon. This is something that is used in Sensei and also used in DAMIC. So these have very small target masses, but they also have the lowest dark matter threshold, and they are most sensitive to dark matter particles with a mass of around 10 MeV. There is argon, which is used in dark side 50. This has a mid-range target mass, and they have a mid-range dark matter mass threshold. So they are mostly sensitive to most sensitive to dark matter masses of around 50 MeV. And finally, there is xenon. So they have the largest target mass for these search strategies. However, they also have the heaviest dark matter thresholds, and they are most sensitive to dark matter masses of around 200 MeV. Note that all of these plots have been drawn by assuming the standard halo model of dark matter velocity distribution. However, we know from we are starting to know from various observations, mostly by Gaia and also by other experiments, also by other telescopes like LAMOST, that probably there are also dark matter substructures near the solar circle, and these can also have an effect on dark matter electron scattering, especially in xenon-based dark matter detectors. And there's something work that we did some time ago in trying to study these things. And people have also studied how modifications to the dark matter halo velocity distribution can affect these limits. Now, if you look at this plot, this is the same plot shown you can ask a very simple question: how to probe heavier dark matter masses. Note that this plot stops at 1000 MeV, that is 1 GeV, and you can ask what happens at heavier masses. Well, at heavier masses, these limits continue with 1 over m chi. We know what is the dark matter density in the solar circle, given the dark matter mass is m chi. So the number density of dark matter particles that is hitting your detector goes as 1 over m chi. And that's what these limits continue at higher masses. You can ask, well, is there a way to improve this sensitivity at higher masses? Well, the answer is yes. It's very obvious. If you increase the exposure of these experiments, that means if you build a bigger detector and run it for a longer time, then obviously you will be able to probe lower dark matter electron scattering cross sections. So at this point, let's just pause and discuss what are the various exposures that are used in various experiments. So dark side 50 has an exposure of something like 12,000 kilogram days. Sensei has an exposure of 530 gram days. Damichem has an exposure of 85 gram days. And Xenon 1 ton has an exposure of 22 ton days. So you can ask, is there a dark matter detector with a larger exposure? Well, the answer is yes, the sun. And this is the major part of my talk, where I'll try to convince you that the sun as a dark matter detector has tremendous potential. First of all, the sun has orders of magnitude larger exposure. It has been moving through the dark matter halo of the Milky Way during its entire lifetime. And so the exposure, which is the target mass times lifetime, is something like 4.6 solar mass times gigayear. This is much, much larger than what was mentioned in the previous slide. And in this talk, I'll tell you that we can use the sun as a dark matter detector. I mean, dark matter particles can interact with the solar electrons, can get captured, and there are signatures which we can search for using existing data. So the first question is, do dark matter particles interact with the sun? The answer is yes. And this is a small cartoon in order to explain how does this happen. Well, let's assume this is the picture of the sun, and there's a dark matter particle which has a velocity of u chi at infinity. The dark matter particle can get accelerated towards the surface of the sun, gravitationally attracted towards the surface of the sun, and its velocity at the surface of the sun will be this expression, square root of u chi square plus v escape square. This is purely kinematics. And then as the dark matter particle passes through the sun, it is possible that a small fraction of those dark matter particles can scatter with the electrons, provided dark matter and electron have a non-zero scattering cross-section. Here, I denote the scattering cross-section by sigma e. In this scattering, it is possible that the final velocity of the dark matter particles can be less than the escape velocity of the sun. And if that is the case, then the dark matter particles are captured inside the sun. And this process goes on for the entire duration of the age of the sun. So how many dark matter particles are captured inside the sun? Well, this is a capture rate formula. This is sort of very simple. It depends on the total number of solar electrons, which is given by this thing, where NE as a function of R is the number density of solar electrons as a function of radius, and then we do the volume integral. Then obviously it depends on the incident dark matter flux, which depends on the number density of local dark matter, which depends on the dark matter velocity distribution. And then obviously this capture rate also depends on the dark matter electron scattering cross section. And then there is a capture probability, which says what is the fraction of dark matter particles that actually have a velocity less than the velocity of the sun, less than the escape velocity inside the sun, so that they can get captured. So you can do a quick calculation using these formulas, and you will find that if I assume that the dark matter mass is about 100 GeV, and the dark matter electron scattering cross section is something like 10 power minus 39 centimeters squared. Note that this is a number, this is a cross section which is not yet ruled out by laboratory experiments. Then the total amount of dark matter particles that are captured inside the sun is huge. It's something like 10 power minus 17 solar mass. This is roughly the mass of some asteroids that we have. All right. So with currently allowed dark matter parameter space, and there can be an asteroid mass of dark matter inside the sun. And what we are trying to see in this work is how do we probe this dark matter particles inside the sun. So is there a signature? Well, we actually go back to the classic WIMP diagram, where there are two dark matter particles, two asymptotic dark matter particles and two stand model particles in the asymptotic state. In the solar capture, there was one dark matter particle in the initial state, one standard particle in the initial state, which was the electron. And then in final state was also there's one dark matter particle which is captured inside the sun. And then there's another standard particle, which is, again, this is also the electron. So this is the process which leads to capture inside the sun. So then we are trying to see the annihilation signatures. That means these dark matter particles which are formed inside the, which are there inside the sun, can annihilate and produce standard model particles. And the question that you can ask is there a measurable effect of these captured dark matter particles in our detectors? Again, the answer is yes. Can we detect the signature of dark matter inside the sun? The answer is yes. Well, the only thing that will come out from the center of the sun are neutrinos. So neutrinos can be produced inside the center of the sun. So this is a schematic diagram. This is the picture of the sun. This is probably the region. This is the region where the dark matter is captured, the so-called the dark matter core. Dark matter gets annihilated, produce to various standard model particles, and they produce neutrinos, and then the neutrinos will propagate and will reach the Earth. Turns out that the solar core density is 150 grams per cubic centimeter, and its radius is something few times 1.5 times 10 per 10 centimeters. And for a 100 GeV neutrino or an antineutrino, the mean free path is approximately the size of the solar core. So it's plausible that neutrinos and antineutrinos will escape from the center of the sun's radius. In fact, neutrinos and antineutrinos are the only particles which can inform us about the dark matter annihilation signature inside the solar core. So where will these neutrinos come from? Well, these neutrinos will come from a process called electroweak bremsstrahlung. For example, if dark matter annihilates to E plus E minus, you can emit a Z boson from either the electron leg or the positron leg, and this will produce a lot of neutrinos and antineutrinos of all flavors. Electroweak corrections are especially important for dark matter masses of greater than or equal to 500 GeV, and there is a large amount of literature dedicated to study these electroweak corrections for various dark matter annihilation channels. How does the neutron spectrum from the sun look like? Well, if this is the neutron mass, neutron energy in GeV, and if this is the DE per GeV, if dark matter particles have a mass of 1 TeV and they're annihilating to E plus E minus, we are looking at the nu bar spectrum. So this solid line is the neutron spectrum without propagation, and due to propagation, that means due to absorption inside the sun and other effects, this is the spectrum that you see, this dotted line. So as you can see, there is a dramatic effect on the spectrum due to propagation effects inside the sun. One can also show that at least in the parameter space that we are talking about, the capture rate of dark matter and the annihilation rate are in equilibrium. So you can relate the annihilation rate to the capture rate of dark matter divided by 2. Obviously, the neutron and antineutron flux is given by this expression. So how do we detect these neutrinos? Well, we can detect these neutrinos by using the IceCube neutron telescope. IceCube is a gigaton effective volume neutron detector at South Pole. IceCube has been running for more than a decade, producing fantastic results. IceCube detects neutrinos via the chain curve light that is emitted as charged particles are produced due to neutron charge current or neutral current interactions. The typical threshold of IceCube is 100 GeV. However, there is something called DeepCore inside IceCube, which can detect neutrinos with energies as low as 10 GeV. So let's come to the results. Well, so this is the idea. So this is a schematic diagram of IceCube. This is the sun. A neutron is being emitted due to dark matter annihilation. It produces, say, a muon track inside IceCube, and the angle between the muon track and the neutron direction is theta sun. And what we can do is we can plot cos theta sun in the x-axis and the number of events in IceCube in the y-axis. Let's take the dark matter mass to be 10 power 3 GeV and the dark matter electron scattering to be 10 power minus 37 centimeters squared. This is the background due to atmospheric neutrinos. This is the IceCube data. And if dark matter with this parameter space annihilates to tau plus tau minus, this is the histogram that you see. All right. So as you can see, the event number due to new physics is clearly much larger than the observed data. So this data point of dark matter mass scattering cross section with this annihilation channel is ruled out. So this is how we get the constraints on new physics. So you can look at constraints on dark matter electron scattering using this technique. Let's first talk about dark matter annihilating to E plus E minus. Again, what is plotted on the x-axis is dark matter mass in GeV, and the dark matter electron scattering cross section is plotted on the y-axis in centimeter square. This is the limit from the xenon 1-ton experiment, and our limit is given by this blue line, right? So as you can see that our derived limits are comparative with xenon 1-ton, assuming E plus E minus dark matter annihilation final states, and it's obvious that these limits will improve with near future data from various IceCube upgrade, KM3net, and other neutron telescope data. And there's a tremendous discovery potential of this technique using this guaranteed dataset that is coming up. We also plot the neutron mist, which is basically the neutrons produced from cosmic ray interactions inside the sun. If dark matter annihilates to tau plus tau minus, then our limits are even stronger. Again, dark matter mass on the x-axis, dark matter electron scattering cross-section on the y-axis. This is the limit from xenon 1-ton. This is an old limit from the Super Kamiokande experiment, and our limits are given by this line, by this line, and again by this line. Again, anything above is ruled out. So as you can see, our derived limits are more than order of magnitude more stringent than xenon 1-ton, assuming tau plus tau minus dark matter annihilation final states. And again, as I said, with near future data sets from various neutron telescopes, there is a tremendous discovery potential using this technique. Finally, what happens if dark matter gets captured via electron scattering but is analyzed to nu bar? Again, we use the same technique. We use the existing IceCube dataset to probe, again, dark matter mass on the x-axis, dark matter electron scattering on the y-axis. This is the xenon 1-ton limit in the dashed line. This is the old limit from Super Kamiokande experiment. And these three lines are the limits that we derive from existing dataset of IceCube and DeepCore. Again, as you see, that our limit is the most stringent constraint on dark matter electron scattering cross-section is more than an order of magnitude more stringent than xenon 1-ton experiment, assuming dark matter annihilates to nu bar. And again, the guaranteed data set that's coming from existing and near future neutron telescopes will improve these limits and maybe discover dark matter. So with this, I conclude my talk. I hope I've convinced you that in order to discover dark matter, we must probe all regions of dark matter parameter space and all different couplings of dark matter standard model particle. We study how dark matter can get captured inside the sun via electron scattering and use high energy neutrinos to probe various dark matter annihilation final states. For various final states, we derive the most stringent bound on dark matter electron scattering cross-section. And the near future guaranteed data set coming from various different neutron telescopes, which are either running or under construction, have the potential to discover dark matter interaction using this technique. Thank you very much.